where do we normally use, let's say, related rate of change? So, for an example, if let's say you guys were doing civil engineering, so in a case, let's say when it comes to, let's say the bridge is there. So there's something that we talk about. Let's say maybe we talk about the beams which are supporting this, let's say the UDL, the uniform distributed load of the tar road there. So that's what we call at some point is deterioration. Let's say there's corrosion, I want to say. So if there's corrosion bit by bit, it is losing, let's say, certain particular, let's say some of the parts of the walls we are losing some content there. So sometimes even corrosion, what happens at some of the materials that were in there, if let's say it's exposed to water or it's exposed to, let's say, any chemicals, we keep on losing, it's peeling off. So a related rate of change, you apply it there. So now to determine at what rate maybe we are losing the area of, let's say, the beam or the volume. In any cases, even if, let's say, you have expansion, let's say, remember in bridges you have connections there. So in the bridges you have interconnections. At some point, the more you have cars, at maybe at what rate do we have, let's say, the connection of the joints there? So maybe, let's say, we have 16 cars per second, or maybe we have applied maybe, let's say, 50 kilograms per second. Therefore, there's this connection which is happening there. So in many cases, we apply related rates of change, even when it comes to, let's say, now your maximization. If, let's say, you want to build a house, so you need to know how much of material you have to use and what price it's going to cost you. So we know that they say maybe per room, maybe you can spend 2,000 rents. So if you've done the proper calculations, bricks, cement, roofing, it will cost this much. Which sizes that you must have. So that is the reason that we apply, let's say, calculus, those cases. So it's applicable in many cases, even in economics to even understand the markets. Sometimes if the oil is sold at this price and then the cost of a barrel maybe per day is this much. So sometimes we can predict maybe in future even in markets. So that's why when we forecast the market to see the repo rate going up and down, it's based on the projection. So it is we are using those type of or let's say calculus. But not to waste time, I want to give down the formula here, 1 over 3 pi r squared and multiplied by h. So there's something that we need to note. Let's say, for example, maybe if we're given h equals to 3r. Let's say we're given 3r. Oh, shit. So let's say we're given 3r. So normally we need to identify sometimes the volume. The volume is dependent to what? So the volume, let's say this volume of what? Is it for a sphere or is for what? Phone. It's a phone, eh? Yeah, this is a cone. Remember, it's a cone. So it is a volume of a cone. It is a volume of a cone. So, so a cone we need to understand is dependent to which variable. So it's dependent to R and it's dependent to H, isn't it? So if let's say maybe if we can reduce the size of the radius of the cone, even the volume does reduce, isn't it? And if we recreate, even the height, if you reduce the height, then the volume changes. So which means in some cases when we are doing calculations or design, let me just put the cone though. So if let's say we're talking by a case now of filling in, a case of filling in, let's say water, if let's say we're putting water in that cone, or let's say ice cream to say. So if you keep on consuming it, I want you to see something here. So if let's say it's this point and that point, so let's say it's a small height, let's say maybe let me give this, can I give this H2, H1, but the initial height, we give a capital H. So if let's say we check, the more maybe if let's say we take the, let's say we eat our ice cream, let's hope it's a cone that, I don't know, it could fit like this. Let's hope it's a cone where let's say maybe it's solid. Let me not talk about ice cream cone. Let me talk about fuel. Let's say petrol. If let's say we have filled in, let's say fuel there, we open up here, then we'll see the volume decreasing of, let's say the fuel going down. So I hope you see that even the radius is changing here. So if we're at this point here, we'll have a radius there. And let's say the height, let's say H2. Can say maybe this is R1, this will be R2. The more you empty it, the more, let's say, the height reduced and the radius is reduced until we have zero. So imagine it in that way that, oh, for this one, for a cone, for the volume is dependent to the radius and 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 the height. So where you need to read the questions or statements when you are solving problems. But let's practice differentiation. Let's say we want to determine, um, yeah, let's say we want to derivate or change the volume. Let's say we change the volume in terms of R. Let's say we change the volume in terms of R. So if we change the volume in terms of R, which means we're going to keep H constant. We leave it as constant. But what we're going to do, let's first substitute the R that is given there. H is equals to R. So if let's say we have 1 over 3 pi R squared. So we said H is 3R. So we have V there is equals to 1 over 3. We have pi. Uh, so this is H, therefore multiply. I think this is going to be eliminated. Therefore, we're going to have R cubed, isn't it? Times 3. So allow me to say 1 there. Because when I multiply 1 over 3 times 3, it is 1. So we have pi R cubed. So let us derivate V in terms of R. So we're going to say dV over dR. We're changing for the volume in terms of R. So therefore it's equals to, we'll have pi. So derivate R in terms of R. We're going to have what? 3 R squared, isn't it? So we have 3 R squared. So we're changing the volume in terms of R. So hence, change in volume over change in the radius R. So I want to put, if let's say maybe we have to change, let's change in terms of H. Let's say V in terms of H. Let's find dV over dH. So for easier case, you can keep R now as constant because we are saying now we need to change the volume in terms of H. You can keep R as constant then derivate in terms of H. But as we're given what is H is equals to 3 over R, and what will be R? R will be equals to H over 3. So I want us to derivate in terms of H now. So we leave the function in terms of H, 1 over 3 pi. Therefore, we'll have H over 3. Where am I substituting? I substituted in the wrong part. So therefore v is equals to 1 over 3 pi. So I want to substitute the value of r there. So it's h over 3 to the power of 2 times h there, the original equation. So but let's simplify into standard form. So I see I have h squared times h to give me h cubed. And then 3 squared is 9, isn't it? Isn't it? 3 squared is 9. And I'm looking into times 3, it would be 1 over 1 over 3 times 9. 1 over 3 times 9. So it is 1 over 3 times 1 over 9. I get this is 1 over 9. I hope you see it, because this 3 is in the denominator. So 1 over 3 times 1 over 9 is 1 over 27. So pi h cubed. So now we can change the volume in terms of h, dv over dh, which is going to be equals to. So in terms of h, we derivate, these are constants, pi and 1 over 27 are constants. So we're going to have 3 times 1 over 27, which is going to be 1 over 9, isn't it? Therefore, pi h squared, subtract 1 from h. So 3 times 1 over 27, it is 1 over 9, then pi h squared. Okay. I hope that is clear. I want to answer another question here. So, let's say we want to change volume in terms of time. We want to change volume in terms of time. The volume changes in terms of time. So this comes to the initial state that I was talking about, because this thing changes in terms of time. If let's say per second the fuel is being emptied, the radius is changing, the height is changing. So, which means in terms of time, maybe per second, maybe might have h1, then h2. So, the original function, so let me do this first. V is equals to 1 over 3 pi r squared times h. So I hope you know that, as we said, v is dependent to h and r. So when we're going to derivate, please note that we change both in terms of time. They change in terms of time. So volume changes in terms of time. It means that these two, we have to change them in terms of time. So it's product of two functions. You think of product rule. If the volume changes per second, if the volume changes, let's say per second or per minute, what is happening to the radius in terms of time? What is happening to the height in terms of time? So it has to change too, because volume is dependent on both variables. So what we're going to do, we look into these are constants, 1 over 3, and pi are constants, but these are functions of volume, are functions of volume. I know you're used to x and y in implicity, but here we have the same. So this is product of two functions. So what we're going to do, let me factor out pi over 3, or pi over 3. So we're going to derivate r in terms of time. So it will be 2r, therefore change it in terms of time. It's dr over dt. So dr over dt. And we need to multiply by what? By the first function, which is the second function, which is h. Which is h. Okay, allow me to put this, though it's not good way to put it. So it is plus now. In the second term, we are going to multiply by r squared, but we're going to derivate h or change h in terms of time. Derivative of H in terms of time is going to be dh over t. So we're not changing it in terms of h, we're changing it in terms of time. So that's why it's dh over dt. So that's what we'll be having. You're changing that in terms of time. Okay, I think.